Welcome back to the next video, everybody. Today is going to be about Selmer groups. And just a quick update, my semester starts tomorrow, so I will probably be slightly changing my upload schedule to be something like Monday through Thursday. Okay, so anyways, let's get on with the video. So local conditions. Let's let X be a G sub Q module. So it is an abelian group acted on by the absolute Galois group of Q. Recall from last video, we want to study elements of H1 GQX with various imposed local conditions. So we have to make that precise, okay? Because elements here with various local conditions imposed on them correspond to certain equivalence classes of infinitesimal deformations, okay? So for each place L of Q, including the Archimedean place, so the prime at infinity, in other words, we know that we may regard the group G sub L, so the absolute Galois group of Q sub L, as a subgroup of G sub Q. This goes way back to the beginning of the playlist on Fermat's last theorem that I've created, okay? So of course, this means we have restriction maps res sub L from H1 of GQX to H1 of G sub L of X, because G sub L's are all subgroups of G sub Q. Okay, let's let this kind of cal L, which will denote a family of L sub L's, big L sub little L's. Let's let that be a family of subgroups, big L sub little L, in H1 of G sub L X, as L runs through all the places of Q. Okay, now we're going to impose one restriction on this family of subgroups, though. I want big L sub little l to be H1 of G sub L mod I sub L, comma, X to the I sub L for all but finitely many L. In other words, I want big L sub little l to just be the unramified classes for all but finitely many L. This is a common theme in number theory in general. We want things to be unramified for all but finitely many places, okay? I mean, we've been talking about this since the beginning of the playlist. And so when we have this setup, when we have such a family of subgroups inside these guys here, we're going to call it such a family a collection of local conditions. Okay, so a generalized Selmer group is H1 sub cal L of QX, and that will denote the set of all X in H1 of GQX, such that res sub L of X is in big L sub little l for all little l. So in other words, you're taking things here that restrict to the big L sub little l's here for all primes L. Okay, so that's what a Selmer group is. Okay, and so we're going to let cal L star be the collection of all the big L sub little l perps, where big L sub little l perp is the annihilator of big L sub little l under the Tate pairing from local duality from last video. Okay, and then by theorem 1, we know that this perp is H1 of G sub L mod I sub L X star to the I sub L for all but finitely many L. Okay, we talked about this. We figured out the exact annihilators of unramified classes under the Tate pairing. Okay, so here's a crucial result. This is used in Wiles' proof, and we will use this. We have used this whether or not you realize it. Theorem 2. It turns out that if cal L is a collection of local conditions, then H1 sub cal L of QX is finite always. And more importantly, the size of H1 sub cal L of QX over the size of H1 sub cal L star of QX star equals the size of H0 of GQX over the size of H0 GQX star times this product over all primes L less than or equal to infinity over the size of big L sub little l over the size of H0 of GLX. Okay, now before you get too far into trying to use this result to do things, you have to make sure this product actually makes sense. But remember, lemma 1 from a previous video says that the size of H0 of G sub L X is the same as the size of H1 of G sub L over I sub L X to the I sub L. And so that means because most of the big L sub little l's are exactly this H1 group here, there's going to be a cancellation here, and we'll get 1 for almost all primes L. And so this product essentially is a finite product. Okay, so it actually makes sense. It converges. It converges because it's a finite product. Okay. All right, so just some quick remarks here. First of all, this formulation of theorem 2 isn't quite the same one that shows up in Wiles' paper and Wiles' proof, but theorem 1 and proposition 3 from previous videos immediately show that they're equivalent. So I'll let you investigate that yourself. That's just a technical point. The version that I gave here is from the DDT notes. If you'd like a proof, you can start by looking at CSS page 117. The proof is difficult. It uses some hard results from Tate found in Milne's arithmetic duality, chapter 1, We will talk more extensively about this result in chapter 14. Right now, I'm just kind of giving it to you. Okay, and then I also wanted to make a comment about how this result is used typically in practice. What you do is you choose your local conditions cal-L, typically in such a way that H1 sub cal-L star is 0. So you want this guy to be trivial. You want this guy to have size 1. And then the point is, all of this stuff on the right-hand side is, in almost all cases, incredibly easy to compute and handle. And so what you get is a bunch of easy to handle stuff, something that's trivial, and then you combine all that together and you instantly get results about H1 sub cal-L, which is actually the goal. You're trying to study local conditions in H1 of QX, right? Remember, that was the goal initially. Okay. And so we'll do a big example of this next time, and we'll be able to start using this to do computations that have directly to do with Fermat's last theorem pretty soon. So thanks for watching, and I'll see you then.